The ocean is an alien world hiding beneath the surface of our own planet. Over 80% of it remains unexplored, and the deeper you venture, the more it resembles another dimension entirely. What lurks in these depths defies imagination, and the creatures that call it home operate by rules so foreign, they seem impossible. Let's begin with something that sounds peaceful. Bioluminescence. The gentle glow of marine life lighting up the darkness. But this isn't a romantic underwater light show, it's a weapon. Deep-sea creatures use light as a form of biological warfare, creating false signals to lure prey into their jaws or to blind predators long enough to escape. The anglerfish dangles a glowing lure in front of its mouth, a living fishing rod that draws victims directly into a trap lined with needle-sharp teeth. The bioluminescent bacteria living in this lure aren't just passengers, they're accomplices in murder. The ocean's depths operate under pressure that would instantly crush the human body. At the deepest point, the Mariana Trench, the pressure is over 1,000 times greater than at sea level. Imagine the weight of 50 jumbo jets pressing down on every square meter. Yet life thrives here, adapted to conditions that would be instantly fatal to surface dwellers. These creatures exist in a world where the laws of physics seem bent to accommodate impossibilities. Consider the vampire squid. Despite its terrifying name, it doesn't actually suck blood. Instead, it has evolved something far more unsettling. When threatened, it turns itself inside out, exposing spines and bioluminescent photophores that create a living constellation of warning lights. It can eject clouds of glowing mucus that hang in the water like ghostly phantoms, confusing predators while it escapes into the void. This creature has mastered the art of becoming a living nightmare. The barrelly fish possesses a transparent head and tubular eyes that can rotate within its skull. It hovers motionless in the water column, looking upward through its see-through cranium, waiting for the silhouette of prey to pass overhead. When it spots a target, those barrel-shaped eyes rotate forward, and the fish rises like a spectre from the depths to claim its victim. The transparency that makes it beautiful also makes it one of the ocean's most efficient predators. Giant tube worms cluster around hydrothermal vents, growing up to 8 feet long without ever seeing sunlight. They have no mouth, no stomach, no digestive system as we understand it. Instead, they've formed a partnership with bacteria that live inside their bodies, converting toxic chemicals into energy. These creatures exist by consuming poison, thriving in an environment that would kill almost any other form of life on Earth. The deep sea is home to living fossils, creatures that have remained virtually unchanged for millions of years. The frilled shark, with its primitive gill slits and eel-like body, is often called a living dinosaur. It strikes like a snake, coiling its body and lunging forward to swallow prey whole. Its teeth are arranged in 25 rows, each one designed to prevent escape once something enters its mouth. Hagfish produce slime that can expand to 10,000 times its original volume in less than a second. When threatened, they release this substance into the water, creating a suffocating cloud that clogs the gills of predators. The slime is so effective that it can turn several gallons of seawater into a thick, choking gel. These creatures can also tie themselves in knots, using their own bodies as tools to gain leverage while feeding or escaping. The giant isopod resembles a massive pillbug, growing up to 20 inches long. These scavengers can survive for years without eating, entering a state of dormancy that borders on death. When food finally arrives, usually in the form of a whale carcass drifting down from the surface, they gorge themselves until their bodies distort from the sheer volume of flesh they consume. Siphonophores are not single creatures, but floating colonies that can stretch longer than blue whales. Each individual in the colony has a specialized function, some for propulsion, others for feeding, still others for reproduction. They drift through the water like living cities, trailing tentacles armed with millions of stinging cells. These tentacles can extend for hundreds of feet, creating invisible walls of death in the open ocean. The ocean's deepest residents live in a world of perpetual night, where the sun has never shone and never will. Here, in the abyssal plains, creatures move through landscapes of marine snow, the constant drift of organic particles falling from the world above. This snow is made of dead plankton, fecal pellets, and the remains of surface dwellers, creating a macabre blizzard that never stops. Zombie worms bore into the bones of dead whales, dissolving the calcium with acid secretions. These worms have no mouth or stomach, instead absorbing nutrients directly through their skin. A single whale skeleton can support a community of these creatures for decades, creating an oasis of life in the desert of the deep sea floor. The ocean's chemistry itself is alien. In many deep areas, the water contains no oxygen, creating vast dead zones where only specialized bacteria can survive. These regions are expanding as ocean temperatures rise and currents change, creating underwater deserts that grow larger each year. Methane seeps on the seafloor support ecosystems that exist independently of the sun's energy. Here, bacteria consume methane and hydrogen sulfide, chemicals that would be toxic to most life forms. These cold seeps can support communities for thousands of years, creating stable oases in an otherwise sparse environment. The pressure at depth doesn't just crush, it transforms. Gases that exist at the surface become liquids. The very chemistry of life must adapt to these conditions, with proteins and cell membranes that would fail instantly if brought to the surface. These creatures exist in a state that defies our understanding of biological possibility. Deep-sea gigantism affects many species, causing them to grow far larger than their shallow water relatives. Giant spider crabs with leg spans reaching 12 feet scuttle across the sea floor. Colossal squid, larger than any surface predator, battle sperm whales in the crushing darkness. These titans exist in a world where size is survival, and the biggest predators rule territories larger than entire countries. The ocean's thermal vents create underwater geysers that spew superheated water rich in minerals and toxic chemicals. Around these vents, life has evolved to harness energy from chemical reactions rather than sunlight, creating ecosystems that could theoretically exist on other planets. These communities represent an entirely different branch of life's tree, one that suggests how alien worlds might harbour their own forms of existence. Brine pools on the seafloor create underwater lakes with their own shorelines and waves. The water in these pools is so dense with salt and other minerals that it doesn't mix with the surrounding seawater. Fish can swim above these pools, as if flying over an alien landscape, and anything that ventures too deep into the brine dies almost instantly from the toxic concentration of chemicals. The ocean's conveyor belt of currents carries water that began its journey at the surface centuries ago. By the time this water reaches the deepest trenches, it has travelled thousands of miles and collected the chemical signatures of every region it has passed through. This ancient water forms the blood of the planet's circulatory system, connecting every ocean and carrying the history of the world in its depths. Creatures in the deep ocean live according to different rules of time. Some deep-sea fish can live for centuries, growing slowly in the cold, nutrient-poor environment. Orange roughy can live for over 150 years, making them older than most countries when they're finally caught. The Greenland shark may live for over 400 years, meaning some individuals alive today were born before the American Revolution. The sound of the deep ocean would drive surface dwellers mad. Whale songs that travel for thousands of miles, the grinding of tectonic plates, the crash of underwater avalanches, all combine to create a symphony of the abyss that never stops. These sounds can travel across entire ocean basins, carrying messages between creatures separated by continents. Marine snow doesn't just fall, it creates weather patterns in the deep ocean. Seasonal blooms at the surface create underwater blizzards as dead organisms drift downward. These storms of organic matter can bury entire sections of the seafloor, creating burial grounds for creatures that lived and died in the sunlit world above. The deep ocean is Earth's largest habitat, yet it remains more mysterious than the surface of Mars. We have better maps of distant planets than we do of our own sea floor. Every expedition into these depths reveals new species, new ecosystems, new impossibilities that challenge our understanding of what life can become. And perhaps most unsettling of all, the ocean is rising. As ice caps melt and thermal expansion occurs, the alien world beneath the waves grows larger, claiming more of the land-based world we know. The boundary between our realm and theirs shifts constantly, bringing the mysteries of the deep ever closer to our shores. The creatures of the abyss don't just live in another world, they are another world. They represent billions of years of evolution along paths so divergent from our own that they might as well be aliens. Yet they share our planet, existing in the vast spaces beneath our feet, in a realm where darkness reigns eternal and the impossible becomes routine. In the deepest places of the ocean, where pressure creates diamonds and heat births new forms of life, existence continues according to rules we're only beginning to understand. These depths hold secrets that could redefine our understanding of life itself, offering glimpses into the kinds of worlds that might exist in the dark spaces between stars. The ocean remembers everything. Every extinction event, every climate change, every moment in Earth's history is recorded in the sediments of the deep sea floor. These archives stretch back hundreds of millions of years, creating a library of planetary memory that dwarfs any human record. The ocean floor holds secrets that dwarf any mystery on land. Deep beneath the waves, in trenches so profound they could swallow entire mountain ranges, lie formations that challenge everything we thought we knew about our planet. These are not mere depressions in the seafloor, but active, breathing wounds in the Earth's crust, constantly reshaping themselves through forces we barely comprehend. Consider the Puerto Rico Trench, a gaping chasm in the Atlantic that plunges over 8 kilometers into darkness. Here, the ocean floor doesn't simply drop away, it tears itself apart, creating underwater canyons that dwarf the Grand Canyon. The water pressure at these depths is so intense that it would crush a human body in milliseconds, yet life persists in forms so alien they seem borrowed from another world entirely. But trenches are just the beginning. Scattered across the ocean floor are seamounts, underwater mountains that rise from the abyssal plains like monuments to geological time. These submerged peaks, many taller than Everest, remain largely unexplored. Their slopes harbour ecosystems that have evolved in complete isolation, creating biological laboratories where evolution has taken paths unlike anywhere else on Earth. The most unsettling aspect of seamounts isn't their size, but their movement. These massive formations don't simply sit motionless on the ocean floor. They migrate, carried along by the slow but relentless dance of tectonic plates. A seamount that formed in tropical waters millions of years ago might now rest in polar regions, carrying with it the fossil remains of creatures that once thrived in warmth but died in the cold transition. Between these underwater mountains lie the abyssal plains, vast stretches of seafloor that extend for thousands of kilometers in every direction. These regions, once thought to be biological deserts, teem with life forms that exist nowhere else. The sediment here isn't simply mud and sand. It's a living carpet of microorganisms that process nutrients in ways that fundamentally differ from any terrestrial ecosystem. Within this sediment lies a record of Earth's history more complete than any found on land. Every volcanic eruption, every asteroid impact, every mass extinction event has left its signature in these deep ocean layers. Scientists drilling into abyssal sediments have uncovered evidence of cosmic events so catastrophic they reshaped the entire planet, yet these records remain largely unread, waiting in the darkness. The architecture of the deep ocean follows patterns that seem almost designed. Mid-ocean ridges, the underwater mountain chains where new seafloor is born, stretch for over 60,000 kilometers around the globe. These ridges form a connected system, a single geological feature that dwarfs any mountain range on land. Along these ridges, the Earth literally splits open, pouring molten rock into the cold abyss and creating new ocean floor at a rate of centimeters per year. This process, called seafloor spreading, means the ocean floor beneath your feet right now wasn't there when dinosaurs roamed the Earth. The Atlantic Ocean is still growing, pushing Europe and North America apart at the same rate your fingernails grow. In geological terms, oceans are temporary features, opening and closing like vast breathing cycles that span hundreds of millions of years. But it's the transform faults that truly reveal the ocean's violent nature. These are zones where tectonic plates slide past each other, creating underwater earthquake zones of devastating power. The sound of these underwater earthquakes travels for thousands of kilometers through the ocean, creating acoustic signatures so powerful they can be detected by marine life across entire ocean basins. Marine animals have learned to navigate using these geological sounds, treating earthquake noise as a form of natural GPS. Whales time their migrations to coincide with specific seismic patterns, following underwater sound highways that connect feeding grounds separated by thousands of kilometers. This suggests a level of geological awareness in marine life that we're only beginning to understand. The ocean floor itself breathes, not in any biological sense, but through a process called seafloor venting, where the Earth's crust periodically releases massive volumes of water that has been trapped in rock for millions of years. This ancient water, heated by the planet's core and laden with minerals, erupts from the seafloor, carrying chemical signatures from the Earth's formation. Some of this vented water is older than complex life itself, having been locked in rock since the planet's youth. When it finally escapes, it brings with it dissolved compounds that provide the first hints of what Earth's early oceans might have contained. These chemical time capsules suggest that the early Earth's oceans were radically different from today's, containing dissolved metals and gases that would be toxic to most current life forms. The distribution of these venting systems follows patterns that seem almost intentional. They cluster around certain types of geological formations, creating underwater oases of chemical activity in an otherwise stable seafloor environment. The spacing between vent fields suggests some form of geological rhythm, as if the Earth's crust releases pressure according to a schedule we haven't yet decoded. Between the active geological zones lie the abyssal hills, a landscape of gentle slopes and valleys that covers more of Earth's surface than any other topographical feature. These hills, formed by the cooling and contraction of volcanic rock, create a terrain so vast and repetitive that navigation becomes nearly impossible. Early deep-sea explorers described a sense of vertigo when traveling through these regions, unable to distinguish one hill from another across thousands of square kilometers. The sediment patterns in these areas reveal the ocean's hidden weather systems. Deep ocean currents, invisible from the surface, carve channels and deposit materials in ways that mirror the patterns of rivers and streams on land. These underwater rivers flow for thousands of kilometers, carrying sediment from continents to the deepest parts of the ocean basins, creating underwater deltas and floodplains that remain completely hidden from surface observation. Some of these deep currents are so powerful they can move objects the size of boulders across the ocean floor. The evidence appears as mysterious trails in the sediment, long scratches and grooves that extend for kilometers without any obvious source. These trails suggest the presence of massive objects, rolling along the seafloor, pushed by currents we can't directly observe and following paths that seem to defy the surface ocean's behavior. The temperature of the deep ocean floor remains remarkably stable, hovering just above freezing year-round. This consistency has created environments where time seems suspended. Organic materials that would decay rapidly on land can persist for thousands of years in the deep ocean's cold, oxygen-poor environment. The result is an underwater museum where the remains of surface life accumulate in layers, creating a fossil record of stunning completeness. But this preservation comes with a cost. The same conditions that preserve organic matter also slow biological processes to an almost geological pace. Bacteria in deep ocean sediments reproduce so slowly that a single generation might span human lifetimes. These microorganisms exist in a state somewhere between life and death, maintaining biological functions at such a reduced rate that they challenge our understanding of what it means to be alive. The pressure at the ocean floor creates conditions that don't exist anywhere else on Earth's surface. Water behaves differently under such extreme compression, becoming denser and more viscous, almost syrup-like in its consistency. This altered water creates unique physical environments where normal fluid dynamics break down, allowing for phenomena that would be impossible at surface pressures. Objects sinking to these depths undergo transformations that seem to violate the laws of physics as we understand them at surface pressure. Air-filled containers don't simply implode, they collapse into forms so compact that their original shape becomes unrecognizable. Even solid materials like metal can deform under the relentless pressure, bending and warping in ways that would require tremendous force at the surface. The ocean floor's magnetic properties tell the story of Earth's changing magnetic field over millions of years. As new seafloor forms at mid-ocean ridges, it records the direction and intensity of the planet's magnetic field like a vast geological tape recorder. This record reveals that Earth's magnetic field has reversed hundreds of times throughout history, with north becoming south and south becoming north in patterns that seem chaotic, but may follow rules we haven't yet discovered. During these magnetic reversals, the planet's protective magnetic shield weakens dramatically, allowing cosmic radiation to penetrate much deeper into the atmosphere and oceans. The geological record suggests that some of these reversal periods coincided with mass extinction events, hinting at connections between cosmic forces and life on Earth that we're only beginning to explore. The seafloor's mineral deposits form through processes so slow they're almost incomprehensible. Manganese nodules, potato-sized lumps of metal that litter vast areas of the ocean floor, grow at rates measured in millimeters per million years. These nodules form around tiny nuclei, often a shark's tooth or piece of bone, accreting minerals from seawater with the patience of geological time. Some of these nodules have been growing continuously for tens of millions of years, making them among the oldest objects on Earth's surface. Their layered structure records changes in ocean chemistry over spans of time that dwarf human history, creating archives of environmental change that extend back to when the continents were arranged in completely different configurations. The patterns in which these nodules distribute themselves across the sea floor follow rules that seem almost biological. They maintain spacing from each other as if competing for resources, creating mathematical arrangements that suggest some form of chemical communication between objects that by all rights should be inert. This organization hints at processes operating on scales and timescales that challenge our understanding of how non-living systems can exhibit apparently purposeful behavior. Deep ocean mining operations have begun to disturb these ancient formations, but the full consequences remain unknown. The seafloor communities that have developed around and within these mineral deposits represent ecosystems that have remained stable for millions of years. Their disruption may have cascading effects that won't become apparent for decades or centuries, making every mining operation an uncontrolled experiment in environmental change. The ocean floor continues to reveal new secrets with each expedition into its depths. Recent discoveries include underwater rivers that flow beneath the seafloor, carrying water through networks of caves and channels that extend for hundreds of kilometers beneath the ocean bottom. These hidden waterways suggest that the boundary between the solid Earth and the ocean is far more porous and dynamic than previously imagined. The temperatures, pressures, and chemical compositions found in these deep environments continue to reshape our understanding of the limits of life itself. Each expedition returns with evidence of biological processes that shouldn't be possible according to our current scientific models, yet clearly occur in the alien landscape of the deep ocean floor. This underwater realm, vast beyond comprehension and largely unexplored, represents perhaps the greatest frontier remaining on our planet. The ocean floor harbors one of the most disturbing geological phenomena known to science. Massive underwater landslides, called submarine avalanches, can move billions of tons of sediment at speeds exceeding 60 miles per hour. These catastrophic events reshape entire ocean basins in minutes, generating tsunamis that dwarf any surface disaster. The most terrifying aspect is their unpredictability. The continental shelves are riddled with unstable sediment deposits, poised like loaded weapons, waiting for the slightest trigger to unleash devastation across thousands of miles of seafloor. Beneath the Pacific Ocean lies a graveyard of tectonic violence known as the Ring of Fire. This horseshoe-shaped zone contains 75% of the world's active volcanoes, many lurking unseen beneath miles of water. Underwater volcanic eruptions create their own hellish environment, where superheated water and toxic gases form deadly plumes that can extend for hundreds of miles. The pressure at these depths prevents water from boiling despite temperatures exceeding 1,000 degrees Fahrenheit, creating a liquid inferno that would instantly vaporize any living creature unfortunate enough to encounter it. The ocean's memory runs deeper than human civilization. Locked within ice cores and sediment layers lie records of mass extinction events that wiped out 90% of marine life. The Permian extinction, known as the Great Dying, turned the oceans into acidic wastelands devoid of oxygen. Hydrogen sulfide gas bubbled up from the depths, poisoning the atmosphere and creating purple seas of death. These events remind us that the ocean's apparent stability is an illusion. The same forces that once sterilized the planet continue to operate beneath the waves, patient and inexorable. Deep ocean currents operate like a planetary circulatory system, but one that can suddenly and catastrophically shift. The thermohaline circulation, driven by differences in water temperature and salinity, has collapsed before in Earth's history. When this happens, entire regions can be plunged into ice ages within decades. The current that warms Europe could shut down completely, transforming the continent into a frozen wasteland. These circulation patterns are so massive and interconnected that disrupting one can trigger a cascade of climate chaos across the globe. Within the ocean's depths lie underwater rivers and lakes, bodies of water so dense with salt that they flow along the seafloor like liquid mercury. These brine pools are toxic to most marine life, creating underwater deserts where nothing can survive. Fish that swim into these invisible boundaries die instantly, their bodies preserved in the hypersaline environment like specimens in formaldehyde. Some of these underwater lakes stretch for miles, hidden valleys of death in the abyssal plains, where the only movement comes from the occasional rain of organic matter drifting down from the surface world above. The ocean's role as Earth's primary heat engine creates weather patterns of unimaginable power. Hurricanes are merely the visible manifestation of the ocean's thermal energy, but beneath the surface, massive underwater storms rage unseen. These deep water tempests can persist for months, creating underwater tornadoes that spiral down into the abyss. The energy contained in these systems dwarfs human comprehension, capable of moving water masses the size of entire countries across ocean basins. When these forces occasionally breach the surface, they reshape coastlines and alter weather patterns across continents. Perhaps most unsettling is the ocean's capacity for sudden, dramatic change. Throughout history, the seas have experienced rapid transitions that occur faster than ecosystems can adapt. Ocean acidification, driven by carbon absorption, is currently proceeding at a rate 10 times faster than during the worst extinction events in Earth's history. The chemistry of seawater is shifting so rapidly that shell-forming organisms are beginning to dissolve in their own environment. This invisible transformation is turning the ocean into a corrosive bath that could collapse marine food webs within decades. The deep ocean trenches serve as gateways to Earth's interior, where the planet's surface descends into the molten realm below. These subduction zones are planetary recycling centers, where oceanic crust is consumed and reformed in processes that span millions of years. The immense pressures involved can trigger earthquakes so powerful they shift the Earth's axis and alter the length of days. The grinding of tectonic plates generates heat and pressure sufficient to transform rock into magma, feeding the volcanic systems that continuously reshape the ocean floor. In the deepest parts of the ocean, water itself behaves differently. Under extreme pressure, the familiar liquid takes on properties that seem to defy physics. Ice can form at temperatures well above freezing, creating crystalline structures that exist nowhere else on Earth. These exotic phases of water create environments so alien that they challenge our understanding of chemistry itself. Life in these regions must contend not only with crushing pressure and eternal darkness, but with water that follows entirely different rules than the substance we know from the surface world. The ocean's sediment layers tell a story of cosmic violence that spans billions of years. Embedded within the seafloor are the remains of asteroid impacts, volcanic super-eruptions, and magnetic field reversals that sterilized vast regions of the planet. These geological archives reveal that Earth's history is punctuated by catastrophes so severe they reset the evolutionary clock. The ocean has witnessed the rise and fall of countless ecosystems, each one believing itself permanent until the next catastrophe swept it away. The ocean's depths harbor phenomena that defy our surface understanding, where life and death dance in ways that would seem impossible above. In the crushing darkness, miles beneath the waves, creatures have evolved strategies for survival that blur the lines between cooperation and predation, revealing a world where the rules of existence operate on entirely different principles. Consider the vampire squid, whose name suggests horror, but whose reality is far stranger. When threatened, this deep-sea dweller doesn't flee or fight. It turns itself inside out, exposing rows of spines that transform it from prey into something resembling a living nightmare. This isn't aggression. It's pure survival theatre, a biological magic trick performed in the eternal night of the deep ocean. Even more unsettling are the zombie worms, creatures that exist solely to consume the bones of fallen whales. These microscopic engineers bore through calcium structures that should be impenetrable, secreting acids that dissolve bone from within. They transform death into life, creating intricate tunnel systems that can persist for decades, turning whale skeletons into apartment complexes for creatures that feed on decay. The deep ocean's relationship with death extends beyond individual organisms to entire ecosystems built around catastrophe. When a whale dies and sinks to the ocean floor, it creates what scientists call a whale fall, a temporary oasis of abundance in the food desert of the deep sea. These carcasses can sustain unique communities for years, progressing through distinct stages of decomposition, each supporting different species adapted to feed on specific types of decay. The first stage attracts mobile scavengers, sleeper sharks that can live for centuries, hagfish that tie themselves in knots to gain leverage while feeding, and amphipods that swarm the carcass like underwater locusts. This feeding frenzy can last for years, stripping away soft tissue and exposing the underlying structure. The second stage belongs to the bone specialists. Bacteria begin breaking down the lipids trapped within whale bones, creating a chemical environment so specialized that entire families of organisms exist nowhere else on Earth. These creatures have evolved specifically to thrive in the toxic soup of decomposing whale oil, turning poison into sustenance. The final stage transforms the skeleton into a reef-like structure, hosting organisms that feed on the remaining chemicals leaching from the bones. Some of these communities can persist for a century or more, making whale falls among the longest-lasting deep-sea habitats known to science. But perhaps the most disturbing aspect of deep-sea survival isn't how creatures handle death. It's how they handle life itself. In the crushing darkness where food is scarce and encounters are rare, reproduction becomes a matter of life or death strategy that often blurs the line between the two. Take the anglerfish, where males exist solely to find females and literally fuse with their bodies. The male's digestive system dissolves, his circulatory system merges with hers, and he becomes nothing more than a reproductive organ attached to her body. Multiple males can attach to a single female, creating a living reproductive collective that ensures species survival in an environment where finding a mate might be impossible. This isn't romance, it's biological desperation elevated to an art form. The male sacrifices his individual existence for the chance to pass on his genes, while the female carries multiple mates as permanent passengers. It's a strategy that only makes sense in a world where the alternative is genetic extinction. Even stranger are the creatures that exist in a state of suspended animation, neither fully alive nor completely dormant. Tardigrades, microscopic water bears, can survive in the vacuum of space, withstand temperatures that would instantly kill most organisms, and remain dormant for decades before returning to active life. When conditions become impossible, they essentially stop being alive without dying, entering a state called cryptobiosis, where biological time stands still. These strategies reveal a fundamental truth about deep-sea existence. Survival often requires abandoning conventional definitions of life and death. In the deep ocean, organisms exist in states that our surface-based understanding can barely comprehend, neither fully individual nor completely collective, neither entirely alive nor completely dormant. The most unsettling aspect of these survival strategies is how they challenge our assumptions about consciousness and identity. When an anglerfish male fuses with a female, what happens to his individual consciousness? When a creature enters cryptobiosis for decades, does it experience the passage of time? These questions have no clear answers because they push against the boundaries of what we consider possible. The deep ocean forces us to confront the possibility that our surface-based understanding of life, death, and consciousness might be just one limited perspective on existence. In the crushing depths, where pressure can liquefy bones and darkness is absolute, life has found ways to persist that seem more like science fiction than biology. These creatures exist in a world where the normal rules don't apply, where survival strategies that would seem like horror stories become everyday reality. They remind us that life is far more adaptable, more creative, and more willing to embrace the impossible than we ever imagined. In the deep ocean's eternal night, existence itself becomes fluid, transforming in ways that challenge everything we thought we knew about what it means to be alive. The ocean's depths continue to reveal new forms of existence that push the boundaries of biological possibility, each discovery forcing us to expand our understanding of life itself. In the deepest reaches of our planet's waters, where sunlight has never touched and pressures could crush human bones like paper, lies a realm that defies everything we think we know about life itself. This is the abyssal zone, a landscape so alien and hostile that it makes the surface of Mars seem hospitable by comparison. Picture a world of perpetual midnight, where temperatures hover just above freezing, and the weight of 4 miles of water above creates pressures over 1,000 times greater than what we experience at sea level. Here, in this crushing darkness, life not only survives, but thrives in ways that challenge our understanding of what's possible. The ocean floor at these depths is a graveyard of mysteries. Sediments accumulate grain by grain over millions of years, creating layers that preserve the history of our planet like pages in an ancient book. Within these deposits lie clues to mass extinctions, climate changes, and geological events that shaped the world we know today. But perhaps most unsettling is what these sediments reveal about the creatures that call this place home. In the abyssal plains, where the seafloor stretches endlessly like an underwater desert, bizarre formations rise from the depths. Underwater mountains called seamounts pierce the darkness, their slopes teeming with life forms so strange they seem pulled from science fiction. These isolated peaks act as islands in a sea of mud, each one developing its own unique ecosystem, cut off from the rest of the world for millions of years. The creatures that inhabit these depths have evolved in ways that seem to mock the laws of biology as we understand them. Giant tube worms, some reaching lengths of 8 feet, cluster around hydrothermal vents where superheated water, rich in toxic chemicals, spews from the Earth's core. These worms have no mouths, no stomachs, no digestive systems. Instead, they survive through a partnership with bacteria that live inside their bodies, converting the poisonous chemicals into food through a process called chemosynthesis. Nearby, fields of giant clams the size of the dinner plates filter nutrients from water so toxic it would kill most surface life in minutes. These creatures can live for centuries, growing slowly in the perpetual cold, their shells becoming monuments to endurance in one of Earth's most hostile environments. Some specimens discovered are estimated to be over 500 years old, meaning they were alive when Shakespeare was writing his plays. But the hydrothermal vents themselves are perhaps the most alien feature of this underwater world. These underwater geysers create oases of life in the desert of the deep sea, but they're also incredibly unstable. The water they spew can reach temperatures of over 750 degrees Fahrenheit, hot enough to melt lead. The surrounding water, just inches away, remains near freezing. This creates a thermal gradient so extreme that creatures living here must navigate between scalding death and frozen paralysis. The chemistry around these vents reads like a poison inventory. Hydrogen sulfide, the same gas that gives rotten eggs their smell, exists in concentrations that would be lethal to surface life. Heavy metals like copper, zinc, and iron flow freely through the water. Yet life has found a way not just to tolerate these conditions, but to depend on them entirely. Remove the toxic chemicals, and these ecosystems would collapse. What makes this even more extraordinary is that these vent communities exist in complete isolation from the sun. While virtually all life on Earth's surface depends ultimately on photosynthesis, converting sunlight into energy, these deep-sea ecosystems run entirely on chemosynthesis, deriving energy from chemical reactions. It's as if we've discovered an entirely parallel tree of life, one that operates by completely different rules. The predators in this realm are equally extraordinary. The vampire squid, despite its terrifying name, is actually a gentle filter feeder, but its appearance is the stuff of nightmares. When threatened, it turns itself inside out, exposing rows of spines and creating a display so alien it seems designed by a malevolent intelligence. Its eyes, proportionally the largest of any animal on Earth, are adapted to capture even the faintest traces of bioluminescence in the absolute darkness. Speaking of bioluminescence, the deep sea is a galaxy of living stars. Creatures here produce their own light through chemical reactions, creating displays that would put any fireworks show to shame. But this isn't for beauty, it's for survival. Some use light to lure prey, others to confuse predators, and still others to communicate across the vast darkness. The anglerfish dangles a glowing lure in front of its massive jaws, waiting for curious prey to investigate what appears to be food, but is actually a death trap. Perhaps most unsettling are the creatures that seem to exist in a state between life and death. Zombie worms, officially known as oceanics, literally eat bones. When a whale dies and its carcass sinks to the ocean floor, these worms colonize the skeleton, boring into the bones and consuming them from the inside out. The largest specimens are female, while the microscopic males live as parasites inside the females' bodies, existing solely to reproduce. A single whale skeleton can sustain these creatures for decades, becoming a metropolis of the macabre. The frilled shark, often called a living fossil, represents another form of temporal horror. This creature has remained virtually unchanged for 80 million years, meaning it would have been familiar to the dinosaurs. Its primitive jaw can unhinge like a snake's, and its needle-sharp teeth are designed to prevent any prey from escaping once caught. Encounters with these creatures are so rare that each sighting makes international news, reminding us how little we know about what lurks in the depths. But perhaps the most disturbing aspect of the deep ocean is how little of it we've actually explored. We've mapped more of the surface of Mars than we have of our own ocean floor. Less than 5% of the ocean has been directly observed by humans, meaning that 95% of our planet's living space remains a complete mystery. Every deep-sea expedition discovers new species, new ecosystems, new mysteries that challenge our understanding of life itself. Recent discoveries have only deepened these mysteries. Scientists have found evidence of vast underwater rivers, where dense, salty water flows along the ocean floor like surface rivers flow across land. These underwater waterways can stretch for hundreds of miles, carrying nutrients, sediments, and life forms across the abyssal plains. Some of these rivers are so large they dwarf the Amazon, yet they flow in complete darkness, unseen and unknown until just recently. Even more bizarre are the deep-sea brine pools, underwater lakes of water so dense with salt and other chemicals that they form distinct boundaries with the surrounding seawater. These pools are toxic to most marine life, yet they support their own unique ecosystems around their edges. Fish swimming into these pools become disoriented and often die, creating an underwater graveyard around each brine lake. The pressure at these depths creates phenomena that seem to defy physics. Materials that are rigid at the surface become fluid under the immense pressure. The water itself becomes denser, more viscous, behaving more like oil than the water we know. Gases that would normally bubble to the surface are compressed into liquid form, creating underwater rivers of liquid methane and carbon dioxide. This pressure has forced deep sea creatures to evolve in ways that seem impossible. Many fish at these depths have no swim bladders, the gas-filled organs that help surface fish control their buoyancy, because any gas-filled organ would be crushed instantly. Instead, they've developed other methods of staying neutrally buoyant, often filling their bodies with low-density oils or developing cartilaginous skeletons that are more flexible than bone. The giant isopods, relatives of pillbugs that can grow to the size of footballs, scuttle across the ocean floor like armored tanks. These creatures can survive for years without eating, slowing their metabolism to almost nothing when food is scarce. When they do find food, usually the carcass of a large animal that has sunk from above, they can gorge themselves to the point where they become too heavy to move, sometimes dying from overeating after years of starvation. The ocean's deepest trenches, like the Mariana Trench, represent the ultimate frontier of our planet's mysteries. At depths of over 36,000 feet, these trenches cut into the Earth's crust like wounds that never heal. The pressure at the bottom of these trenches is over 1,000 times greater than at sea level, equivalent to having 50 jumbo jets stacked on top of every square inch of your body. Yet even in these most extreme environments, life persists. Xenophyophories, single-celled organisms that can grow to the size of dinner plates, create intricate structures on the trench floors. These creatures are among the largest single-celled organisms known to science, defying everything we thought we knew about the limits of cellular life. They build delicate, glass-like shells that somehow withstand the crushing pressure, creating underwater sculptures of impossible beauty in a place where no human eye can see them. The deepest parts of the trenches remain largely unexplored, not because we lack the technology, but because the conditions are so extreme that even our most advanced submersibles can only make brief visits. Each expedition to these depths costs millions of dollars and risks equipment worth more than most people's houses. Yet the few glimpses we've gotten suggest that the deepest parts of our ocean may harbour life forms so alien that they could redefine our understanding of biology itself. Recent technological advances have begun to reveal the true scope of deep-sea biodiversity. Genetic analysis of water samples suggests that there may be millions of species living in the deep ocean that science has never documented. Each deep-sea expedition discovers an average of 1 new species per day, and these are just the creatures large enough to be easily noticed. The microbial life in the deep ocean represents an entire unseen universe of organisms, many of which may have biochemistries unlike anything found elsewhere on Earth. Some of these microorganisms live in the sediments of the ocean floor, where they've been buried for millions of years. These ancient communities of bacteria exist in a state of suspended animation, their metabolism slowed to almost nothing, dividing perhaps once every 1,000 years. They represent the ultimate survivors, having endured in their buried world since before complex life existed on land. The deep ocean also serves as Earth's largest carbon reservoir, storing vast amounts of carbon dioxide in its depths. As our planet's climate changes, understanding these deep-sea carbon cycles becomes crucial for predicting our future. But the deep ocean's role in climate regulation extends far beyond carbon storage. The deep-sea currents that flow along the ocean floor help drive the global circulation patterns that regulate weather around the world. These deep currents move incredibly slowly, taking centuries to complete their circuits around the globe. Water that sinks into the depths in the polar regions may not return to the surface for 1,000 years or more. This means that changes in deep ocean circulation can have effects that don't become apparent for generations, making the deep sea both a buffer against rapid climate change and a potential source of long-delayed climatic surprises. The mineral wealth of the deep ocean is staggering. The seafloor is carpeted with nodules of manganese, copper, nickel, and other valuable metals. These nodules form over millions of years as metals precipitate out of seawater, creating potato-sized lumps of concentrated ore scattered across the abyssal plains. Some estimates suggest that these deep-sea nodules contain more metal than all known land-based reserves combined. But harvesting these resources would require destroying some of the most pristine and least understood ecosystems on Earth. The slow growth rates of deep-sea organisms mean that any disturbance to the seafloor could take centuries or millennia to recover. We face the prospect of destroying habitats before we even know what lives in them, potentially erasing species that could hold keys to understanding life's limits and possibilities. The deep ocean continues to challenge our assumptions about life's boundaries. Scientists have discovered organisms living at temperatures that should cook them, pressures that should crush them, and in chemical environments that should poison them. Each discovery expands our understanding of where life might exist, not just on Earth, but potentially on other worlds with extreme environments. These findings have profound implications for astrobiology, the search for life elsewhere in the universe. If life can thrive in the crushing depths of our oceans, feeding on chemicals and surviving without sunlight, then similar life might exist in the subsurface oceans of moons like Europa or Enceladus. The deep sea has become our laboratory for understanding how life might persist in the most unlikely places throughout the cosmos. As we continue to explore these depths, each expedition reveals new mysteries that dwarf our previous understanding. The deep ocean remains our planet's final frontier, a realm so vast and alien that it humbles even our most advanced technology. In its crushing darkness, life has found ways to flourish that challenge everything we thought we knew about the possible, reminding us that our planet still holds secrets that may take centuries to fully understand. The abyss gazes back at us with eyes we're only beginning to perceive, through senses we're only starting to comprehend, in an environment so removed from our experience that it might as well be another world entirely. Looking at the seafloor's extreme conditions and mysterious depths, we encounter organisms that have mastered survival in ways that challenge our understanding of life itself. But there's something even more unsettling lurking in these abyssal plains. Creatures that blur the line between living and dead, between parasite and predator. Meet the zombie worm, a creature so bizarre that when scientists first discovered it, they couldn't believe what they were seeing. These aren't your typical deep-sea dwellers. Zombie worms don't hunt, they don't scavenge, and they don't photosynthesize. Instead, they do something far more disturbing. They consume the bones of dead whales that have fallen to the ocean floor. When a whale dies and its massive carcass sinks to the seafloor, it creates what marine biologists call a whale fall, an oasis of nutrients in the food desert of the deep ocean. For months, sometimes years, this single carcass sustains an entire ecosystem. First come the hagfish and sleeper sharks, stripping away the soft tissue. Then smaller scavengers pick at the remaining flesh. But when everything edible is gone, when nothing remains but a skeleton of bone, that's when the zombie worms arrive. These creatures, scientifically known as oceanics, have evolved one of the most macabre feeding strategies on Earth. The female worms, which can grow several inches long, bore directly into whale bones using acid secretions that dissolve the calcium. But here's the truly unsettling part. They don't just eat the bone surface. They drill deep tunnels, creating elaborate root-like structures that extend throughout the skeleton, slowly dissolving it from the inside out. The males of the species are even stranger. They're microscopic, living their entire lives as parasites inside the females' bodies. Dozens of these tiny males can live within a single female, existing solely to fertilize her eggs. They have no digestive system, no way to feed themselves. They're essentially living sperm factories, completely dependent on their female hosts. What makes zombie worms particularly eerie is how they transform the whale skeleton. A bone that once supported tons of living whale becomes a haunted architecture, riddled with tunnels and chambers where these creatures live and breed. The skeleton becomes a city of the dead, inhabited by organisms that exist in a space between life and decay. But zombie worms represent just one example of the ocean's necrophagic ecosystem, organisms that have specialized to consume death itself. In the deep sea, where nutrients are scarce and every calorie counts, death becomes just another resource to be exploited. Consider the hagfish, a primitive eel-like creature that's remained virtually unchanged for over 300 million years. When they encounter a dead or dying animal, they don't just feed on it, they burrow inside it. Hagfish can tie themselves in knots to gain leverage as they tear chunks of flesh from inside their prey. They can strip a large fish to bone in a matter of hours, working from the inside out like living digestive systems. Even more disturbing are the organisms that specialize in consuming the dead in the ocean's deepest trenches. In places like the Mariana Trench, where pressure exceeds 1,000 times that at sea level, specialized bacteria and other microorganisms break down organic matter in ways that seem almost alchemical. They transform death into life through chemical processes so alien that they might as well be taking place on another planet. The ocean's relationship with death goes deeper than individual scavengers. Entire ecosystems are built around mortality. Marine snow, the constant rain of dead organisms, fecal matter, and organic debris that drifts down from the surface, forms the foundation of deep-sea food webs. This biological fallout creates layers of sediment on the seafloor that contain the compressed history of death in the ocean, stretching back millions of years. In some regions, the seafloor is carpeted with the shells and bones of countless dead organisms, creating vast underwater graveyards. These bone beds and shell deposits tell stories of mass extinctions, climate changes, and the rise and fall of entire species. The seafloor itself becomes a library of death, each layer a chapter in the story of life's fragility. But perhaps most unsettling of all is how the ocean processes human death. When bodies enter the ocean, whether through shipwrecks, accidents, or burial at sea, they become part of this vast necrophagic system. The same organisms that consume whale falls and fish carcasses don't discriminate. Organic matter is organic matter, regardless of its origin. The ocean's relationship with death reveals something profound about marine ecosystems. Unlike terrestrial environments, where death often leads to rapid decomposition and recycling of nutrients, the ocean can preserve death for centuries or even millennia. The cold temperatures, high pressure, and lack of oxygen in deep waters can mummify organic material, creating underwater time capsules that preserve the moment of death indefinitely. This preservation has given scientists unique insights into the ocean's history. But it also means that the seafloor is littered with the perfectly preserved remains of organisms that died thousands of years ago. In some deep-sea trenches, researchers have discovered wood from trees that fell into the ocean centuries ago, still intact and slowly being consumed by wood-boring organisms that specialize in processing this ancient organic matter. The ocean's necrophagic organisms have also evolved remarkable partnerships with death itself. Some deep-sea bacteria have developed the ability to detect the chemical signatures released by dying organisms from vast distances. They can sense a whale fall from miles away and begin the journey toward it, following chemical trails through the darkness like underwater vultures drawn to carrion. These organisms don't just consume death, they celebrate it. When a large carcass falls to the deep sea floor, it triggers what marine biologists call a feeding frenzy that can last for decades. The area around a whale fall becomes one of the most biodiverse ecosystems in the deep ocean, supporting hundreds of species that exist nowhere else on Earth. The zombie worms and their fellow necrophages represent evolution's solution to the ocean's greatest challenge: how to extract life from death in an environment where energy is precious and opportunities are rare. They've turned the ocean floor into a vast recycling center where nothing is wasted, where every death becomes the foundation for new life. But these creatures also remind us of something darker about the ocean's nature. In the deep sea, the line between life and death becomes blurred. Organisms exist in states that seem to defy our understanding of what it means to be alive. They metabolize so slowly that years can pass between meals. They exist in conditions that would kill most life forms instantly. They've adapted to thrive in an environment that resembles the void of space more than any earthly habitat. The ocean's necrophagic ecosystem forces us to confront uncomfortable truths about life's persistence in the face of death. In the deepest parts of our planet, death isn't an ending. It's a transformation, a resource, an opportunity. The zombie worms boring through whale bones, the hagfish burrowing through carcasses, the bacteria consuming organic matter in the trenches. They've all found ways to extract life from death, to build thriving communities around mortality itself. This relationship between death and life in the ocean reflects something larger about our planet's biosphere. The boundary between living and non-living, between organism and environment, between life and death, is far more porous than we typically imagine. In the ocean's depths, these boundaries dissolve entirely, creating ecosystems where death feeds life in an endless, macabre dance that has continued for billions of years. The zombie worms and their deep-sea companions represent life's ultimate triumph over death, not by avoiding it, but by embracing it, by finding ways to thrive in death's very presence. They've turned the ocean floor into a realm where death becomes life, where endings become beginnings, and where the very concept of mortality takes on new meaning. In the end, these necrophagic organisms remind us that the ocean operates by rules fundamentally different from those of the terrestrial world. It's a realm where death doesn't end life's story, but continues it, where organisms have evolved to see opportunity in mortality, where the seafloor becomes a vast, dark garden fertilized by the endless rain of death from above. And perhaps that's the most unsettling truth of all, that in the ocean's depths, death isn't the opposite of life. Deep in the abyssal plains, where sunlight has never touched and pressures could crush a human instantly, lies one of the ocean's most haunting phenomena. Whale falls. When a massive whale dies and sinks to the seafloor, it becomes something far more significant than just another corpse in the deep. It transforms into an oasis of life in the most barren landscape on Earth. The journey begins when the whale's body settles onto the seafloor, sometimes miles beneath the surface. Within hours, creatures emerge from the darkness. Hagfish, those primitive eel-like scavengers, arrive first. They burrow into the carcass, feeding from the inside out, their bodies writhing through tunnels of decomposing flesh. Sleeper sharks, moving like ghosts through the black water, tear away massive chunks with their serrated teeth. But this is just the beginning. The whale fall will support life for decades, perhaps even a century or more, transforming through distinct stages of decay. First comes the mobile scavenger stage, where anything capable of movement in the deep sea converges on this unexpected feast. Amphipods swarm the bones in numbers that defy imagination, sometimes covering every surface in a writhing carpet of tiny bodies. As the soft tissue disappears, the whale fall enters its enrichment stage. The oils and fats that have seeped into the sediment around the carcass create a nutrient-rich environment that supports entirely different communities. Polychaete worms, some species found nowhere else on Earth, colonize the area. These aren't ordinary worms. Many are giants by deep-sea standards, their bodies adapted to process the chemical soup that surrounds the decomposing whale. The most extraordinary stage comes last, when only the bones remain. This is when the whale fall reveals its true secret. The bones themselves become a source of energy through a process so alien it seems like science fiction. Bacteria living within the bones break down the lipids stored in the whale's skeleton, creating hydrogen sulfide in a process similar to what happens at hydrothermal vents. This chemical energy supports an entire ecosystem of creatures that never depend on sunlight, even indirectly. Tube worms sprout from the bones like a macabre garden, their bodies housing chemosynthetic bacteria that convert the whale's remains into usable energy. These bone-eating worms, or oceanics, are among the strangest creatures in the ocean. The females are the ones you see, boring into the whale bones with acid secretions, while the microscopic males live as parasites inside the females' bodies. What makes whale falls truly unsettling is how they connect the surface world to the deep, in ways we're only beginning to understand. A whale that fed in Arctic waters might carry pollutants accumulated over decades to the deepest parts of the ocean. Heavy metals, microplastics, and industrial chemicals become concentrated in the whale's tissues, then distributed throughout the deep-sea food web as the carcass decomposes. Some whale falls have been discovered with plastic debris still visible in the whale's stomach, a haunting reminder that even in death, these giants carry the evidence of humanity's impact on the oceans. The creatures that feed on these contaminated carcasses incorporate these pollutants into their own bodies, creating a pathway for surface contamination to reach the most remote ecosystems on Earth. The spacing of whale falls across the ocean floor isn't random. Scientists estimate that in healthy whale populations, these carcasses would be distributed roughly every 5 to 10 kilometers across the deep sea floor. This creates stepping stones of specialized habitat, allowing rare deep-sea species to spread from one whale fall to another across vast distances. But as whale populations have declined, these stepping stones have become more widely spaced, potentially isolating populations of whalefall specialists. Recent discoveries have revealed that some whalefall communities can persist for over 100 years on a single carcass. The largest whales, blue whales, and fin whales create the most long-lasting ecosystems. Their massive skeletons can support unique communities for generations of deep-sea creatures. Some of the tube worms found on ancient whale falls are estimated to be decades old, having spent their entire lives in the chemical garden created by a single whale's death. Perhaps most disturbing is how whale falls reveal the ocean's capacity for recycling death into life in the most efficient ways possible. Nothing is wasted. Even the whale's teeth become substrate for specialized organisms. The calcium carbonate in the bones slowly dissolves, altering the chemistry of the surrounding water and sediment in ways that can persist long after the last traces of organic matter have disappeared. The discovery of whale falls has fundamentally changed how we understand deep-sea ecosystems. Before we knew about these oases of death, scientists assumed the deep ocean was largely uniform, a vast desert punctuated only by the rare hydrothermal vent. Now we know the seafloor is dotted with these islands of intense biological activity, each one a complex ecosystem built entirely on death and decay. What's truly haunting is that we've only discovered a tiny fraction of the whale falls that must exist on the ocean floor. For every one we've found and studied, thousands more lie undiscovered in the darkness, supporting communities of creatures we've never seen. Each one is a time capsule, preserving not just the whale's own story, but the story of the ocean itself during the whale's lifetime. The bacteria that break down whale bones have revealed secrets about life's ability to extract energy from the most unlikely sources. These organisms represent some of the most ancient forms of life on Earth, using chemical processes that may have sustained life billions of years ago, before photosynthesis evolved. In the darkness around whale falls, life operates on principles that predate the sun's role in Earth's energy budget. As climate change alters ocean chemistry and temperature, whale falls are becoming laboratories for understanding how deep-sea life might adapt to changing conditions. The acidification of seawater affects how quickly whale bones dissolve, potentially shortening the lifespan of these deep-sea oases. The warming of deep waters could alter the bacterial processes that make whale falls such productive ecosystems. The study of whale falls has also revealed how some of the ocean's most specialized creatures have evolved to depend entirely on death. Some species of bone-eating worms are found nowhere else but on whale carcasses. Their entire evolutionary history is tied to the death of giants. If whale populations continue to decline, these species face extinction not because their habitat is being destroyed, but because it's no longer being created. In the deepest parts of the ocean, where the pressure would instantly crush any surface dweller, these monuments to death continue their slow transformation. The whale's journey from living giant to deep-sea ecosystem spans decades, creating a bridge between the sunlit surface waters where it once lived and the eternal darkness where it now serves as the foundation for an alien world. The haunting beauty of whale falls lies in their reminder that in the ocean, death is never truly the end. It's a transformation, a passing of energy from one form of life to another, played out in the darkness over timescales that dwarf human experience. The deep ocean operates on principles that defy human intuition, where the familiar rules of surface existence simply cease to apply. In these lightless depths, pressure becomes a creative force rather than a destructive one, sculpting life forms that challenge our understanding of what's possible. The bathypelagic zone, beginning at 1,000 meters, marks the threshold where sunlight becomes extinct. Yet this darkness harbors ecosystems more complex than many terrestrial environments. Consider the phenomenon of pressure adaptation in deep-sea organisms. At depths of 4,000 meters, pressure reaches 400 times that at sea level, equivalent to having 50 jumbo jets stacked on every square meter of your body. Yet creatures like the barrelé fish have evolved transparent heads filled with fluid, allowing their tubular eyes to rotate upward to spot the silhouettes of prey against the faint shimmer of bioluminescence above. Their skulls are essentially windows, a biological solution so alien it seems designed by nightmare rather than nature. The ocean's thermal layers create invisible boundaries as rigid as walls. The thermocline acts as a liquid ceiling, trapping warm surface water above and maintaining the deep ocean at temperatures just above freezing. This thermal stratification has remained stable for millions of years, creating distinct worlds stacked atop one another, like floors in a skyscraper made of water. Each layer hosts its own specialized community, rarely interacting with the others, except during the daily vertical migration, when trillions of organisms rise from the depths to feed at the surface under cover of darkness. Deep-sea gigantism reveals itself in creatures that grow to impossible sizes in the abyss. The giant tube worm, thriving near hydrothermal vents without any connection to sunlight, can reach 8 feet in length despite lacking a mouth, stomach, or anus. Instead, its body cavity houses billions of chemosynthetic bacteria that convert toxic hydrogen sulfide into energy. The worm essentially farms poison-eating bacteria in its own flesh, surviving on the metabolic waste of its internal ecosystem. The vampire squid, despite its ominous name, represents one of the ocean's most elegant solutions to deep-sea survival. When threatened, it inverts itself inside out, displaying bioluminescent photophores like a living constellation, while its protective spines create an impenetrable barrier. This creature exists in the oxygen minimum zone, where oxygen levels drop so low that most marine life cannot survive. Yet the vampire squid has adapted to extract enough oxygen from this hostile environment to maintain its ghostly existence. Hydrothermal vent communities operate on principles that revolutionize our understanding of life's requirements. These oases of activity in the deep ocean floor create their own weather systems, with superheated water reaching 400 degrees Celsius erupting from the Earth's core. The mineral-rich plumes support entire ecosystems based not on photosynthesis, but on chemosynthesis, where bacteria convert chemicals like hydrogen sulfide and methane into energy. These communities exist in perpetual winter, yet they burn with activity fueled by the planet's inner fire. The discovery of whale falls has revealed that death in the deep ocean becomes the foundation for new life. When a whale dies and sinks to the sea floor, its carcass becomes a resource island that can sustain specialized communities for decades. The decomposition occurs in predictable stages, first attracting mobile scavengers, then supporting bacterial mats that feed on the whale's lipids, and finally creating a reef-like structure as the whale's bones become colonized by tube worms and other organisms that feed on the oils slowly seeping from the skeleton. Brine pools in the deep ocean create underwater lakes with shores, surfaces, and currents distinct from the surrounding seawater. These hypersaline pools are toxic to most marine life, yet their edges teem with specialized organisms that feed on the chemicals dissolved in the brine. Fish swimming into these pools become instantly disoriented and often die, their bodies preserved in the high-salt environment like specimens in formaldehyde. The pools maintain their integrity for years, creating permanent underwater deserts in the midst of the ocean. The deep scattering layer, a phenomenon that puzzled early sonar operators, represents the largest migration on Earth. Each night, trillions of organisms rise from the depths toward the surface to feed, creating a false seafloor that appears on sonar screens. This biomass, consisting primarily of lanternfish, krill, and other small organisms, represents more living tissue than all terrestrial wildlife combined, yet it remains largely invisible to surface observers. Abyssal storms, massive underwater weather systems, can persist for months in the deep ocean. These storms transport nutrients, sediments, and organisms across vast distances, creating underwater hurricanes that reshape the sea floor. The storms generate currents powerful enough to move boulders and carve channels in the abyssal plains, yet they occur in complete silence and darkness, invisible to the surface world above. The ocean's memory manifests in its deep currents, which carry water masses on journeys lasting hundreds of years. Water that sank in the North Atlantic during the Little Ice Age is only now reaching the deepest Pacific trenches. These currents transport not just water, but chemical signatures, nutrients, and even microorganisms on globe-spanning voyages that connect every ocean basin in a slow-motion circulation system that regulates the planet's climate. Deep-sea coral reefs, built without sunlight, create three-dimensional habitats in the abyss, using only the sparse nutrients filtering down from above. These cold-water corals grow for centuries, building structures that rival tropical reefs in complexity while existing in perpetual winter. The reefs support diverse communities of fish, crustaceans, and other organisms that have never experienced sunlight, creating underwater rainforests in the planet's most hostile environment. The phenomenon of marine snow, a constant precipitation of organic matter falling from the surface, provides the foundation for all deep-sea life. This underwater snowfall consists of dead plankton, fecal pellets, and organic debris that drifts downward in an endless blizzard of nutrients. The journey from surface to sea floor can take weeks, and most particles are consumed before reaching the bottom, making the deep ocean a place where organisms compete for falling scraps in a vertical ecosystem based entirely on gravity. Seamount communities exist as isolated islands of life rising from the abyssal plains. These underwater mountains create their own microclimates, with unique currents and upwelling patterns that support endemic species found nowhere else on Earth. Many seamounts host communities so isolated that they have evolved into living museums, preserving ancient lineages that have disappeared elsewhere in the ocean. The deep ocean's role as Earth's largest carbon sink reveals its critical function in regulating planetary climate. The ocean absorbs approximately 30% of human-produced carbon dioxide, much of which sinks to the depths where it remains trapped for centuries. This invisible service comes at a cost, as the absorbed carbon increases ocean acidity, potentially dissolving the shells and skeletons of deep-sea organisms and fundamentally altering marine chemistry. Methane seeps on the seafloor create chemical oases where specialized bacteria convert methane into energy, supporting tube worm gardens and clam beds in an environment that would be toxic to surface life. These seeps can persist for thousands of years, slowly releasing greenhouse gases from deep within the Earth's crust, while supporting ecosystems that exist nowhere else on the planet. The deep ocean remains Earth's final frontier, less explored than the surface of Mars despite covering more than 60% of our planet's surface. Every expedition to the abyss reveals new species, new ecosystems, and new phenomena that challenge our understanding of life's limits. In the depths of our oceans, where light never reaches and pressure could crush a human body in milliseconds, something extraordinary happens. Here, in what we might call Earth's final frontier, life doesn't just survive. It thrives in ways that challenge everything we thought we knew about existence itself. Welcome to part 9 of our journey through the ocean's most terrifying and fascinating secrets. We've travelled from the surface waters down through the crushing depths, witnessing creatures that seem pulled from nightmares and ecosystems that operate by rules completely alien to our own. Now, as we conclude this exploration, we find ourselves at the very edge of what science can explain, where the ocean reveals its most profound mysteries and forces us to question the very nature of life on Earth. The deep ocean operates as a biological laboratory, unlike anywhere else on our planet, where the normal rules of chemistry, physics, and biology are rewritten by extreme conditions. Here, in the deepest trenches and most isolated basins, evolution has crafted solutions so radical, so utterly foreign to surface life, that they blur the line between the possible and the impossible. Consider the vampire squid, a creature that exists in the ocean's oxygen minimum zones, regions so depleted of breathable gases that they would kill most life forms within minutes. Yet this ancient creature, unchanged for millions of years, has developed the ability to survive on oxygen levels so low they would suffocate even the hardiest fish. When threatened, it doesn't flee or fight. It turns itself inside out, transforming into a spiky alien ball that drifts through the water like some cosmic entity that has wandered into our world. But the vampire squid's survival strategy reveals something even more unsettling about the deep ocean. It's a window into Earth's past and possibly its future. The oxygen-poor waters where it thrives mirror the conditions that existed in ancient oceans before photosynthesis filled our atmosphere with the gas that most life depends on. As climate change drives ocean deoxygenation, these dead zones are expanding, potentially returning vast portions of our planet to conditions that favour creatures like the vampire squid over the marine life we know today. This isn't just evolution. It's a glimpse into alternative forms of existence that challenge our understanding of what life can be. In the deepest ocean trenches, scientists have discovered microorganisms that don't just survive without sunlight. They've never encountered it in their entire evolutionary history. These creatures have developed metabolisms based on chemosynthesis, feeding on chemicals seeping from the Earth's crust and creating ecosystems that are completely independent of the surface world. The Mariana Trench, plunging over 36,000 feet below sea level, harbours life forms that exist under pressures more than 1,000 times greater than what we experience at sea level. Here, proteins that would denature and cells that would collapse in our world have been restructured at the molecular level to not just function, but thrive. The very chemistry of life has been rewritten in these depths. Perhaps most unnervingly, these deep-sea creatures have evolved forms of communication and behaviour that operate on principles we're only beginning to understand. The deep ocean is filled with a constant symphony of sounds, clicks, whistles, and calls that travel for hundreds of miles through the water. Some of these sounds have been detected but never traced to their source, suggesting the existence of creatures so large or so alien that they remain beyond our ability to locate or comprehend. The bioluminescent displays in the deep ocean create a communication network that spans entire ocean basins. When deep-sea creatures flash their lights, they're not just hunting or defending, they're participating in a conversation that connects organisms across thousands of miles of dark water. This biological internet, operating in frequencies and patterns we can barely detect, suggests forms of collective intelligence that dwarf anything we see on land. But it's the ocean's role as a planetary memory bank that truly staggers the imagination. Every drop of water in our oceans has circulated through this global system countless times, carrying with it chemical signatures and microscopic life forms that preserve the history of our planet. The deep ocean currents, driven by temperature and salinity differences, create a conveyor belt that moves water from the surface to the depths and back again over centuries and millennia. This thermohaline circulation doesn't just move water, it moves life, nutrients and information across the globe. A molecule of water that falls as rain in the Arctic might not see sunlight again for 1,000 years as it travels through the deep ocean currents, picking up and depositing microscopic passengers in a planetary circulation that connects every corner of our world. The ocean's ability to absorb and store carbon dioxide has been protecting us from the full effects of climate change, but this protection comes at a cost. As seawater becomes more acidic from absorbing atmospheric carbon, it's fundamentally altering the chemistry of marine life. Shell-building organisms find it increasingly difficult to construct their protective homes, while other creatures must redirect energy from growth and reproduction just to maintain their basic bodily functions. This ocean acidification is happening at a rate unprecedented in Earth's history, faster even than during the great extinction events that wiped out the dinosaurs. We're conducting a planetary-scale experiment with the ocean's chemistry, and the results are already visible in the changing behavior and survival rates of marine organisms from the tiniest plankton to the largest whales. Yet even as we alter the ocean's chemistry, the deep sea continues to reveal new forms of life that challenge our understanding of biology itself. Scientists recently discovered bacteria living in ocean sediments that reproduce only once every 1,000 years, existing in a state that's barely distinguishable from death, yet maintaining the spark of life across geological timescales. These organisms suggest that life and death, as we understand them, may be far more fluid concepts than we ever imagined. The ocean's deepest trenches serve as natural laboratories, where the extreme conditions create evolutionary pressures that produce solutions impossible anywhere else on Earth. Here, scientists have found organisms that can repair their DNA faster than radiation can damage it, creatures that can survive being frozen solid for months, and bacteria that can metabolize materials that would be toxic to all other known life forms. These discoveries aren't just academic curiosities. They're expanding our understanding of what life might look like on other worlds. The extremophiles of Earth's deep ocean may be our best models for understanding how life could exist in the subsurface oceans of Jupiter's moons or in the methane lakes of Saturn's Titan. The alien life we're searching for in space may be no stranger than the creatures already living in our own planet's deepest waters. The ocean's role as a planetary regulator extends far beyond climate control. The deep sea acts as a massive recycling system, breaking down and redistributing the organic matter that falls from the surface world. Whale falls, the massive carcasses of dead whales that sink to the ocean floor, create oases of nutrients that can sustain entire ecosystems for decades. A single whale fall goes through distinct ecological phases, first feeding scavengers, then supporting bacteria that break down the fats and oils, and finally becoming a reef-like structure that hosts specialized communities found nowhere else on Earth. But perhaps the most profound mystery of the deep ocean lies in its relationship with time itself. In the deepest parts of the ocean, where temperatures hover just above freezing and pressure creates a world unlike anywhere else on Earth, biological processes slow to an almost geological pace. Some deep-sea organisms live for centuries or even millennia, their metabolism so slow that they experience time in ways we can barely comprehend. The Greenland shark, swimming in the Arctic's deepest waters, can live for over 400 years, making it one of the longest-lived vertebrates on Earth. These ancient creatures were alive during the Renaissance, swimming through waters that have remained unchanged for centuries. Their slow growth and extreme longevity mean that some of the sharks alive today began their lives before the United States was founded, carrying within their tissues the chemical signatures of centuries of ocean history. This temporal distortion in the deep ocean creates a world where individual organisms serve as living links between past and future. The oldest deep-sea corals, growing in the darkness of underwater mountains, have been building their skeletal structures for thousands of years, creating archives of ocean chemistry that stretch back through multiple ice ages. These biological time capsules preserve information about past climates, ocean currents, and marine ecosystems that existed long before human civilization began recording history. The deep ocean's relationship with time also manifests in the incredibly slow rate of evolution in these stable environments. These creatures exist as windows into Earth's distant past, showing us what life was like in ancient oceans and providing clues about how life on our planet has responded to previous periods of dramatic environmental change. Yet this stability is deceptive. While the deep ocean changes slowly, it changes profoundly. The shifting of continents over geological time has created and destroyed entire ocean basins, forcing the evolution of new species while driving others to extinction. The deep-sea creatures we see today are the survivors of countless environmental catastrophes, each one having developed the flexibility and resilience necessary to persist through changes that would eliminate less adaptable life forms. The ocean's most terrifying secret may be its ultimate indifference to human existence. We've spent our entire evolutionary history as a terrestrial species, developing technologies and societies adapted to life on land. But the ocean represents a realm so vast and alien that it dwarfs all human experience. The total volume of habitable space in the ocean is hundreds of times greater than all the habitable space on land, yet we've explored less than 1% of this underwater universe. This unexplored realm isn't empty, it's teeming with life forms and ecosystems that operate according to principles we don't understand. Every deep-sea expedition returns with discoveries that force scientists to rewrite textbooks and reconsider fundamental assumptions about how life works. New species are discovered at a rate that suggests millions of unknown organisms still wait in the ocean's depths, each one potentially holding secrets that could revolutionize our understanding of biology, chemistry, or physics. The ocean's alien nature becomes most apparent when we consider the sensory worlds of its inhabitants. In the perpetual darkness of the deep sea, creatures have evolved senses that have no equivalent in our terrestrial experience. Some fish can detect electrical fields generated by other organisms' nervous systems, essentially reading their thoughts. Others navigate using magnetic fields or chemical gradients that are completely imperceptible to humans. The deep-sea anglerfish, with its bioluminescent lure dangling in front of its massive jaws, inhabits a world where light is a tool of deception and death. The patterns and frequencies of bioluminescent displays create a visual language that we can observe but not comprehend, a form of communication that evolved in complete isolation from the surface world and operates according to rules we're only beginning to discover. But perhaps the most unsettling aspect of the ocean's alien nature is how it challenges our understanding of individuality and consciousness. Many deep-sea creatures exist in states that blur the line between individual organisms and collective entities. Siphonophores, often mistaken for jellyfish, are actually colonies of specialized individuals that have become so integrated they function as a single organism. Each individual in the colony has a specific role, Some catch prey, others digest food, still others reproduce, yet none can survive alone. This collective existence reaches its most extreme form in the deep-sea communities that develop around hydrothermal vents and cold seeps. Here, bacteria, archaea, and larger organisms form integrated ecosystems that function almost like superorganisms, with each species playing a role in maintaining the chemical and biological balance necessary for the entire community's survival. The boundaries between species become fluid as organisms exchange genetic material and share metabolic processes in ways that challenge our traditional understanding of biological individuality. The ocean's influence on consciousness extends beyond its alien inhabitants to affect human perception and psychology in profound ways. The few humans who have descended to the deepest parts of the ocean report experiences that are difficult to put into words, a sense of being in the presence of something vast and ancient, of encountering a form of existence so fundamentally different from terrestrial life that it alters their understanding of what it means to be alive. These deep-sea explorers describe the overwhelming silence of the abyss, broken only by the sounds of their own equipment, and the occasional call of an unseen creature. They speak of the way darkness becomes a tangible presence, pressing in from all sides with a weight that goes beyond the physical pressure of the water. Most unsettling of all, they report a sense of being watched, not by any specific creature, but by the ocean itself, as if the entire deep-sea environment possesses a form of awareness that recognizes the intrusion of surface dwellers into its domain. This psychological impact of the deep ocean reflects a deeper truth about our relationship with the marine world. As terrestrial beings, we exist in a thin shell of habitability on the surface of a planet that is overwhelmingly oceanic. The vast majority of our planet's biosphere lies beneath the waves, in environments so alien to our experience that visiting them requires technology that rivals what we use to explore space. Yet we are not separate from this ocean world. The water in our bodies carries the chemical signature of ancient seas. The oxygen we breathe was first produced by marine photosynthesis. The very chemistry of our cells reflects our evolutionary origins in the primordial ocean. We carry the deep sea within us, even as we remain forever excluded from returning to its depths. This connection between human biology and ocean chemistry becomes more poignant when we consider how rapidly we're changing the marine environment. The ocean that gave birth to all life on Earth is being transformed by human activity at a pace that evolution cannot match. The acidification, warming, and pollution of seawater is creating conditions that many marine organisms have never encountered in their evolutionary history. As we alter the ocean's chemistry and temperature, we're not just changing the habitat of marine creatures, we're changing the planetary systems that regulate Earth's climate and make our own existence possible. The ocean's ability to absorb carbon dioxide and heat has been protecting us from the full consequences of our industrial activity, but this protection is not infinite. As the ocean reaches its limits, we're beginning to see changes in weather patterns, sea levels, and marine ecosystems that will reshape life on Earth for millennia to come. The ocean's most terrifying secret may be that it remembers everything. Every ton of carbon dioxide we've pumped into the atmosphere, every degree of warming we've caused, every chemical we've released into the water, all of it is preserved in the ocean's chemistry and biology. The deep-sea sediments contain a record of human impact that will persist long after our civilization has vanished. Future geologists will be able to read in these sediment layers the story of how a single species transformed the chemistry of an entire planet in the space of a few centuries. But the ocean's memory isn't just a record of destruction, it's also a repository of resilience. The same deep-sea ecosystems that preserve evidence of human impact also contain the genetic and biochemical innovations that life has developed to survive previous environmental catastrophes. The extremophiles of the deep ocean, the slow-growing corals of underwater mountains, the ancient bacteria of ocean sediments. All of these represent survival strategies tested over billions of years of Earth's history. As we face an uncertain future on a rapidly changing planet, the ocean's deepest secrets may hold the keys to our own survival. The creatures that thrive in the ocean's most extreme environments have mastered the art of persistence in the face of seemingly impossible conditions. Their biochemical innovations, their energy-efficient metabolisms, their ability to cooperate across species boundaries, all of these represent solutions to challenges that human civilization is only beginning to face. The ocean that seems so alien to our terrestrial experience may actually be showing us what life looks like when it's truly adapted to planetary existence. While we've spent our evolutionary history in the thin shell of habitability at Earth's surface, ocean life has learned to thrive in the vast three-dimensional space that makes up most of our planet's biosphere. As human civilization grapples with resource limitations, environmental change, and the need for sustainable existence, we may find that the ocean's alien wisdom is exactly what we need. In the end, the ocean's most profound secret may be that it's not alien at all. It's home. Not the home we've chosen, but the home that chose us. The ancient environment that shaped the chemistry of our cells and the rhythm of our hearts. Every breath we take connects us to the marine organisms that first learned to split water molecules and release oxygen into the atmosphere. Every heartbeat echoes the tidal rhythms that have pulsed through Earth's oceans for billions of years. The terrifying beauty of the ocean lies not in its alienness, but in its intimacy. This vast, dark, pressure-filled world that seems so hostile to human life is actually the source of everything that makes our existence possible. The ocean's secrets are terrible, not because they're foreign, but because they're familiar. They remind us of what we are, where we came from, and what we might become. As we drift off to sleep, carried by the gentle rhythm of these ocean stories, we might remember that the water in our bodies is still responding to the pull of the moon, still carrying the chemical memory of ancient seas. In our dreams, we might find ourselves swimming through bioluminescent waters, breathing through gills that evolution discarded long ago, speaking in the frequency-rich language of whales and dolphins. The ocean's final secret is that there is no final secret, only an endless depth of mystery that reflects back our own depths, our own mysteries, our own infinite capacity for wonder. In exploring the ocean's darkest places, we discover not alien worlds, but forgotten aspects of our own world, hidden dimensions of the planet that gave us birth and continues to sustain us with every breath, every heartbeat, every dream of swimming in waters deeper and more mysterious than we can ever fully comprehend. And in that endless mystery, in that vast unknown that surrounds our small island of terrestrial experience, we find not terror, but comfort. The knowledge that no matter how much we learn, no matter how far our technology advances, there will always be new depths to explore, new secrets to uncover, new forms of life that challenge our understanding and expand our sense of what's possible in this beautiful, terrifying, alien, familiar ocean world that we call home. Sweet dreams, fellow explorers. The ocean's secrets will still be waiting when you wake.